Magnesium silicide is an interesting inorganic compound consisting of magnesium and silicon. Although it doesn't have many uses, it does have an interesting reaction with aqueous hydrochloric acid. When magnesium silicide reacts with hydrochloric acid, it produces a gas called silane. The silane gas bubbles out of solution, and once it hits air, it spontaneously combusts. Just as a side note, anything that spontaneously combusts in air under a temperature of about 54 degrees Celsius is known as a pyrophoric substance. For this experiment, you'll need 5 grams of powdered magnesium metal, 3.1 grams of sand, and at least a couple hundred milliliters of 10% hydrochloric acid solution. Instead of sand, you could also use silica gel. However, I just have two things to say about silica gel. Before it's used, it must be dried thoroughly because it holds a lot of water, and it must be dried before it's weighed. And secondly, the reaction with magnesium is significantly more violent. So with silica gel, more preparation and care is required, but the final product of magnesium silicide is substantially cleaner and you get a lot more. First, mix about 3.1 grams of sand with about 5 grams of magnesium powder. Then, using something like a glass rod, mix the sand and the magnesium powder together thoroughly. Next, add the mixture to a test tube. Then, add about an equal amount of sand on top of the magnesium sand mixture. This is optional and should not be done if extremely fine sand is used. In this experiment, there will be two reactions that are taking place, and these are shown above. For the first reaction, the magnesium must be ignited. Because sand was mixed into the magnesium powder, the concentration of silicon dioxide around the magnesium powder is much higher than that of oxygen. When the magnesium burns, instead of taking oxygen from the air, it instead strips the oxygen from the silicon dioxide molecule. This will produce magnesium oxide and silicon metal. Depending on how fine your magnesium powder and how fine your sand is, this reaction can be quite violent. The test tube will heat up immensely, and any magnesium remaining will react with the silicon metal that was produced in the first reaction. For this reason, we must use an excess of magnesium metal. The overall reaction is shown above, and from this reaction we can see that you need about 4 times as many moles of magnesium metal as you do silicon dioxide. In terms of mass, this means that the magnesium metal should always be about 1.6 times the mass of the silicon dioxide. The heating up of the test tube is time-lapsed, but the burning of the magnesium will be played in real time. When heating the test tube, it should be pointed away from you at all times. There is a risk of burning magnesium flying out the front. Here I have time-lapsed the cooling of the test tube, and you can see that it slowly cracks as the test tube cools down. Don't worry about this because the magnesium silicide has coated the inside of the test tube and it will prevent it from falling apart. Next, if you use sand, pour out this unreacted sand into a beaker and dispose of it. You could also simply use this sand if you plan to do the reaction again. Next, roll up the test tube in a piece of paper and tape it to keep it from unrolling. Lightly tap your test tube with a hammer just to break the glass apart. Unroll the paper and then start picking out all the broken pieces of glass. You are only trying to remove the big pieces of glass, so don't worry if you leave small pieces of glass behind. The dark black bluish material that you see is actually the magnesium silicide. However, it isn't nearly pure. It contains a lot of magnesium oxide, magnesium metal, and silicon dioxide that didn't react. Once the glass has been removed, you are ready to test out your magnesium silicide. This can be done by dumping a small amount of your product into a 10% hydrochloric acid solution. Here's just a small test to see that it works. The presence of magnesium silicide is confirmed by crackling noises and flames. Next, I poured all of the magnesium silicide into an acid solution. The reaction taking place is shown above. The magnesium silicide reacts with the hydrochloric acid to produce magnesium chloride and silane gas. The silane gas bubbles up through the solution and immediately ignites upon exposure to air. The silane gas reacts with oxygen to reform the much more stable silicon dioxide. A lot of the other bubbling you see is magnesium oxide and unreacted magnesium metal reacting with hydrochloric acid. The final result was enjoyable, but I decided to redo the experiment using silica gel instead of sand. The silica gel is much finer, purer silicon dioxide. If you choose to use silica gel, you'll need to dry it first. This is because it is hygroscopic and it pulls in water from the atmosphere. The reaction between silica gel and the fine magnesium powder is much more violent, and you should not put silica gel or sand on the top. Doing so could cause the test tube to explode. You must allow the expanding gases to escape somewhere. You must also make sure that the heat source is at the bottom of the test tube. If the magnesium closer to the top of the test tube is ignited first, there's a possibility that the test tube can explode. I have actually recorded an example of this happening, and I'll show it to you in a second. This is an example of an improperly placed heat source. It is difficult to tell, but when slowed down, it is possible to see that the magnesium closer to the front of the test tube ignited first. And the undesirable effect is pretty obvious. This is a slowed down shot of the ignition. The use of silica gel allowed for a much better yield of magnesium silicide. The above reaction is much more violent, and only half of the product was used. The silica gel gives a much better yield due to its smaller mesh size, but the preparation is much more dangerous. This is the second half of the magnesium silicide reacting. As with the addition of the first half of the magnesium silicide seems to react quite violently upon addition and then die out quite quickly.